Hey everyone, it's Ken. Today I want to talk to you about the substitution rule for indefinite integrals. And so what I'm going to do, let's jump right in with an example, then we'll explain how to do the process, and then I'll show why this rule is correct. So suppose you're given, let's start out with, I don't know, let's look at maybe cosine of x squared times 2x dx. And so say you want to do this indefinite integral. So after you look at this for a second, you might recognize that the integrand is itself the derivative of something. In fact, if I use the chain rule, the integrand is going to be the derivative with respect to x of what? Maybe sine of x squared. And I'm integrating that. So why is that true? So the derivative of sine is equal to cosine. Plug in the inside function, then multiply by the derivative of that inside function. And so the integral, the indefinite integral of the derivative is just the function itself. So you know that you're going to get sine of x squared plus c. So there's a way to calculate this using something that is called the substitution rule. And I'll show you the technique right now and then explain why is it true. So if you want to rederive this result without having to explicitly recognize that this is just the derivative of the sine of x squared, here's a way that you can do it. You should think of this as like changing the variable. And so your new variable here is kind of your inside function, y equals x squared. So if I set maybe y equals x squared. So I'm looking at this problem and I haven't solved it yet. And then what I can do is, using this differential notation, I can say that dy is equal to the derivative of x squared, that's 2x, times dx. And you can think of that sort of like as bookkeeping if you want. You can think of that as representative, that if you have a small change in y, like a delta y, that's roughly going to be equal to 2x times a small change in x. And instead of putting roughly equal, sometimes we write this in differential form. We just say dy is 2x dx. So then you can go back to this integral. I'll even write it again, clean slate. Cosine of x squared times 2x dx. And you can just directly make these substitutions. So you can say, look, this is equal to integral of cosine of y, because y is equal to x squared. And then if you want, you can replace this 2x dx just with dy. And if you do that integral, you're going to get that cosine of y is equal, the integral of cosine of y is equal to sine of y plus a constant of integration. And well, I want to point out something to you. So in some sense, this is the wrong answer, right? The answer is sine of x squared plus c. But you don't worry about that too much. If you go ahead and make the substitution again, that y is equal to x squared, then you'll get sine of x squared plus c as your final step. And so what's going on here? So if you look at sine of x squared plus c, like, which is your answer? If you make this substitution that y is equal to x squared, I'm almost like doing this process in reverse. If you look at sine of y, sine of y plus c, then you'll realize that the answer is equal to the indefinite integral of cosine of y dy. So there's a little bit of, I don't want to call it trickery, it's more like advanced bookkeeping. You're noticing that the integral of cosine of x squared times the derivative is equal to sine of x squared. That's equal to the integral of cosine of y dy if you then substitute y equals x squared. And the way to keep that straight every single time is to say, look down here, say you're starting with this problem. Go ahead and figure out what you're substituting for. Go ahead and figure out what dy is going to be, and then just literally make that substitution, and then that's how you can do the problem. So I want to show you, first of all, like what's the general formula. So in complete generality, say that you have maybe integral of f of g of x times g prime of x dx. And you'll be thinking of setting y equals g of x, and then dy will be equal to g prime of x dx. And so what I'm saying is, like, this is always going to be equal to the integral of f of y dy, except for the fact that when you do this integral, you'll then have to substitute back y is equal to g of x when you're finished, just like we substituted back y is equal to x squared over there. And why is this little substitution rule going to always be true? It's nothing but integrating that chain rule. So here's a proof, if you like, PF for proof. And what you can do is you can start with your left-hand side. I'm kind of just redoing this whole thing, but in general, you can look at f of g of x times g prime of x dx. So you can rewrite this, if you want, as nothing but the derivative of f composed with g of x. That's the chain rule, dx. Although I guess that's not exactly the derivative, right? Because what you'd have to say is, say you have an antiderivative, like capital F prime is equal to f. Let me just change that a little bit. It's no big deal. So this works when your function has an antiderivative, which will always be true in this class. And so now the chain rule would say that the derivative of this is f prime, plug in g, times g prime, where it's lowercase. And you saw that exactly happen over here in my example, because capital F was sine of x, and lowercase f was cosine of x. They're related because of that derivative. So that's fine. And now the answer is just going to be capital F of g of x. And so why does this kind of prove the theorem? Because if you take y equals g of x, if you rewrite this as capital F of y, so capital F is the antiderivative of lowercase f. So this is just now the integral of f of y dy. And maybe there could be a constant of integration in there. That's OK. So what you're getting now is that this left-hand side is equal to the right-hand side if, once you get to your answer, you make sure to substitute y equals g of x. So that's kind of like the proof for justifying why this substitution rule works, coupled with at least your first example of showing it in practice. But I'll do a couple more examples in another video to give you a flavor of how to do it in practice.